Whoa, hey, sorry about that. I will I will mute that. All right, let's go ahead and click in to get attendance. Oh yeah, wait, hold on. There you go. Okay, so a couple of things while you're clicking in. Uh, Yesterday was the early alert deadline for all faculty members to assess their students, see where they stand in the class. If you had an average below 65 or something, then you got an automatic email that was sent out by the system just to let you know. I then followed up with another email that explained kind of like, well, we haven't even had a test yet. Let's just see how things go. So that's the first thing. Check your email. The next thing is the test. The test is going to be scheduled for, according to our next Thursday, right? So let's see how things go this week. We may meet that. We may actually make that deadline. So let's plan on that. Yes. We will talk about the exam. Yes. We will have a day of discussion. An actual review, like probably. I'll give you something.
Well, back in my remedial class, we did something I put together, like say, you put out the question, and we answer each and every one of us answers it. Like say, Nakash answers 20, and I answer number 5, and so on. And that way, we'll be able to copy it off and explain it.
Well, I don't mind whatever you want to do with the review that I give you. You can do however you want. You know, we won't. I'll provide solutions at some point to it. But here's the thing about reviews. All right, you're getting into grown-up math now. Okay, this is like grown-up math. So what happens is as you go further, the reviews become less and less. In other words, I don't give you a set of problems and say, be able to do exactly these types of problems. I'm just going to change the numbers. That's not what this is about. This is about an understanding of the holistic concepts. So the review could be, in a calculus class, it could be something like, you know, review chapter 1, review chapter 2. You know, it can be that general. And then like Cal 2, Cal 3, there's no review. It's just your review is what you need to study, whatever it is that you need to study to get prepared. And so there's less guidance. That's just part of, you know, preparing you for the classes, engineering classes and stuff. It's like in the real world. How many of you engineers? I have a lot of engineering people here, right? Okay. How many times do you think in the real world, an engineer is faced with the problem, but before their boss gives them the problem, they say, well, look, here's an example of the problem that I'm about to give you worked out. And, you know, if you got any questions, I'll answer that now. Here's a new problem. Go figure it out. That's just not the way it works. Problem solver, being able to study, review, that's a skill, okay? I don't know if I'm addressing. So in this class, I will give some review, but it may not be like in a developmental class where I give you basically the test and I change the numbers. Yeah. Okay. All right, let's get started. Oh, if you're here, oh, I already took the poll. Sorry, too late. Too late. We still have a lot to cover, all right? I know everyone's been emailing me and texting me, you know, wanting to have a quiz, and I'm trying to get you to have a quiz, but I need to get caught up. So my plan is to have a quiz today, but it'll be towards the end. We'll just see. Yeah, we'll just see. We'll just see. Okay? Just pay attention. That would be the best thing you can do for yourself. Okay, we finished up last class. Remember that? We did that assignment together? Or you did that assignment? Do you remember that? Okay. Lights on or off? Great. Okay, just raise your hand real quick. On, off. Okay. Now, I know. Well, there's a lot of stuff that we're going to be looking at today that's visual, and I want to make sure that you can see it, all right? So what I'll do is I'll open these up a little bit, let some more of this sun in. Oops. That a little better? Some natural light. That's not bad. Okay, so let's wrap up 3.3. We want to talk about what's called the average change of a function. Suppose that you have two numbers in the domain of the function, and they aren't the same numbers. Then the average rate of change of the function from A to B is defined to be, average rate of change is equal to, you know what this symbol is right there? That right there? Delta, that means change. That's what we use to represent change. It's the change in the y coordinate divided by the change in the x coordinate. It's rise over run, okay? It's what you've seen in the past for a slope of a line. And it would be f of b minus f of a over b minus a. Now here's the picture. You have a point. That point has an x coordinate of a. The y coordinate is what you get when you plug in a to the function. So you get f of a. The next point is over here. X coordinate is b, y coordinate is f of b. If I want to know the average rate of change between these 2 points, then I will draw a line. And the slope of that line is the rise, which is f of b minus f of a, divided by the run, which is b minus a. We saw this, didn't we? This was difference quotient, wasn't it? This is very much connected to the difference quotient. The only difference is that I'm using a and b instead of what we used before, which was x and x plus h. So this should look familiar. So anytime you have a function, you want to find an average rate of change between 2 points, we will have to compute that ratio right there. So here's an example. And I'm changing the example that was seen in the yellow. There was a typo on your notes. So please change that. I believe I changed the function and I changed part C, and I think I got rid of part D, didn't I? Yeah? Okay. So let's find the average rate of change of this function. I'm going to write it down. The function was 3x cubed minus 5x. I want to find the average rate of change from 0 to 3. So what they've given us here is the a and the b. The a and the b. You can always go with the smaller number, the one to the left, as a and the other one b. That would match up with our picture if you did it that way. So I would say yes. So all I need to do to figure out the average rate of change is figure out what delta y over delta x is, which is f of b minus f of a over b minus a. What is f of b? Well, that's f of 3, right? Minus f of 0 over, what's 3 minus 0? 3? And now I actually have to plug 3 into the function. So plug 3 into the function, let's see what we get. 3 cubed, 27 times 3, 81. Y'all good with that? 81 take away how much? 15. 81 minus 15 is? Got it? Okay. 66. I'm trusting that's 66. Over 3. 66 divided by 3 is 22. The average rate of change is 22. Question, yes? Yeah, we'll probably get something like that in a minute. If it's a fraction, they'll just leave it as a fraction. If you get like 3/4, leave it as 3/4. Yes. That's exactly what we're doing. This is, right here, this is y2, this is y1. We're subtracting them. By the way, I never plugged 0 in, sorry. 0 plugged into the function was what? 0, I just didn't show that. So 66, then you take away nothing, you get 66. Yeah. Plugging 3 into this function for x. Now I want to show you visually what happens, what's happening here, okay? There's our point. What's our first point? X is 0, right? The A is 0. So it's this point, right? The other point is, what is it? Plug in 3. So it's up there, right? 366. That's where it is. And I'm trying to find the slope of that line. And I actually had the computer compute it for me. It's 22. Okay? So you see visually what it is? The 22 represents the slope of that line, connecting those 2 points. It's the average rate of change between those 2 points on the graph. Now let's look at that compared to part B, where we want to go from -1 to 2. So B, we want to go from -1 to 2. So our delta y over delta x will be f of what minus f of what over what? F of 2 minus f of -1 over, careful here, 2 minus -1. Okay? Remember here, A is -1, B is 2. So I'm going f of B minus f of A, bless you, and then B, take away A. Now we have to plug in this stuff, all right? What's f of 2? So let's plug 2 in up here. 2 cubed, 8 times 3, 24. Take away 10, because we're plugging in 2, so what was it, 14? So this is going to be 14 on the top left. Now, be very careful here. F of -1. Plug -1 into the function. What's -1 cubed? -1 still. Times 3? -3. So I'm going to just jot this down. I have -3. And then I'm plugging -1 in here. -5 times -1 would be +5, which would give me a 2, wouldn't it? So when I plug in, uh-oh, I see no all of a sudden. What happened? Well, someone voted. So 14 taking away what? 2 over, what is this? 3. Minus a negative is plus. So 12 over 3 is 4. 12 over 3 is 4. So the slope is 4. Well, it's just plugging 2 into this function. Just go do it on the side, scratch work. This is something that we have to just, you should be able to do on the side if you need to. All right, so what is that one saying? It's saying if I start out at, what, -1 for my x-coordinate, for the A, and then if the other one was where? 4? It's off my graph. Uh-oh, 34. Was it 4? No. It wasn't 4. It was 2, wasn't it? It was 2. There we go. Okay. So now the slope between these 2 points is different than the one before, right? So we get a different value. The slope is 4. All right, let's just take a quick poll if you're good with this or not. All right, the last thing is saying to find the slope from -1 f of -1 to 3 f of -3, or f of 3. So let's see if I can interpret that. I'm trying to go from the point, I forgot already, -1 f of -1 to the point 3 f of 3. This just looks different than before, right? I still have given you the A. I still have given you the B. Right? A is -1, B is 3. I would go like left to right on the number line. the one to the left would be A, the one to the right would be B. So it's the A and B are here, just I didn't write, like in these, I just told you what A and B were. Here they were kind of hidden within the x coordinates of these 2 points. So we just set up the same ratio. It'll be f of what minus f of what over what? So f of 3 first minus f of negative 1 over 3 minus negative 1. So f of b minus f of a over b minus a. F of 3, didn't we figure that out earlier? What was it? Was it 66? Didn't we find out what f of negative 1 was a second ago? Wasn't it 2? Over, what's the bottom? 4. So we get 64 over 4. What's that? 16? Okay. That's it. Any questions? You're good? On a number line, oops, on a number line, negative 1 and 3 are like this. So the one on the left is A, the one on the right is B. Well, no, it's not the larger, it's the formula is always go f of b minus f of a over b minus a. That's what we always do. Okay? Now, that's the average rate of change, okay? Now, we also have the difference quotient. Difference quotient is the same exact ratio, except instead of using A, we use X, and instead of using B, we use X plus H. So I had shown you a picture like this before. Here's a point, right? Here's a point on the graph. Here's a second point. So this point right here, if X here is 1, this second point is 2, then this point, I just added 1 to this one, didn't I? Like I started out X value 1. To get to this one right here, I just added 1, didn't I? But I could move that point over. So let's say there. So the first point is the X is 1. What's the second point? 1.4. So isn't that taking the 1 and adding how much to it? 0.44? So that's what we're saying here. We're going to look at, instead of using A and B, just changing the notation, replacing X for A, and then replacing the B with X plus H. All that happens is the formula turns into this. Okay? Now, look at the way things are worded, though, in this question. Find the slope of the secant line. Slope of secant line, what does that mean? Well, slope of secant line is exactly the same as the average rate of change line. It's the same thing. If you give me 2 points on a curve and you're asked to find the slope of the line between them, it's the slope of what we call the secant line. All right? That's the definition of secant line. It's connecting 2 points on a curve. Okay? So let's see how this is different as far as the mechanics, because look at the way the problem's phrased. They give you a function. They say find the slope of the secant line for x is 1 and h is 0.5. So let's see. So let me write down the function, f of x. I changed the function here. It's x squared plus x plus 1. Part A, let x be 1, let h, not B, h be 0.5. So remember, the formula that I'm going to be using is this, f of x plus h minus f of x all over h. That's the difference quotient. What's x plus h for us here? 1 plus 0.5, which is 1.5. Yeah, that's our b, isn't it? Okay, so this is f of 1.5 minus, now, f of x. What's x? 1. So this is f of 1 all over 0.5. So how would you do this? How would you figure out what 1.5 plugged into this is? You just break out a calculator, right, if you need to. Do 1.5 squared plus 1.5 plus 1. You get a number. I would leave it in decimal. You don't have to. You could turn that into a fraction if you wanted to. But 4.75? I'll take that. I'm not sure. We'll check it in a second. 4.75 minus, now f of 1. So 1 into this should be pretty clean, right? 1 with just 3. All over 0.5. So do the top first. 4.75 minus 3 is 1.75. Divide that by 0.5. And what do you get? What is it? Where are my calculator people? So what I'll do here is I'll just cheat. 3.5. Okay. Okay, now look at the next. Yes. 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 Do this. Well, what do you mean? Oh, yeah, figure out what x plus h is first. So in this case, it's 1 plus 0.5. That'll be given. The x and the h will always be given. Okay? But there's something more subtle here that I want you to realize. All right? I tried to explain last class that what we're interested in calculus is not the secant line, right? It's trying to figure out this tangent line, the line at 1 point. So look, I'm kind of zoomed in on this graph. Do you see this is 1, this is 1.5. These points are pretty close together, right? 1 and 1.5. And the slope between these two lines is what? 3.5. But what if I slide this one closer? What would I be doing? To slide that closer, to slide that closer, wouldn't I just need to make that h smaller? So instead of going 1 and adding 0.5, why don't I add 0.1 instead? I won't be as far away, will I? It would look more like this. So here I'm at 1.5. Let me slide that one to... Keep your eye on the slope, okay? Notice what's happening to it. I'm going to go all the way till I get this to be 1.1. It's looking like it's getting closer to 3, doesn't it? 1.1, right there. 3.1 is the slope. So if we were to do this by hand, so this would be part B. If I were to say let x be 1, let h be, what is it, 0.1 instead of 0.5, then when I set this up and I break out my calculator, I'm going to do f of what? 1.1 minus f of 1 all over 0.1. And when you do that all on your calculator, which I'm not going to do, I'm not going to wait for it. Wait for it. You get 3.1. Trusting that you could figure that out on your calculator. Can I get even closer? Yes. All I need to do is pick a smaller h, right? Like instead of 0.1, 0.01, which means I need to move this instead of being 1.1, it would need to move to 1.01, wouldn't it? And let's keep our eye on this right here. See what happens. Wow, look at, it's getting really close to what? 3. Yes? Now watch what happens when I go one step more. Aren't these going to be the same point? and my computer freaked out, okay? It encountered infinity over infinity, encountered division by 0, didn't it? Because it's the same point. And that's the whole idea here is that even though I can't put the points right on top of each other, I hope for you it's obvious that as I do get closer, the slope of the line is headed towards one thing, and one thing only. And what does it appear that it's headed towards? No, the slope. 3, right? When I'm far out like this, it was 3 point something, but as I get closer and closer, it got closer and closer and closer and closer to 3, right? Closer and closer. So you wouldn't say, yeah, what's going to happen between here and if I got even closer? It's not going to jump to 5, right? It's going to stay in that same pattern. So that's what the calculus will be about, is actually figuring out that the answer is 3. But without doing all the crap we're doing, we'll have a different way. All we're going to do in calculus, we're going to let h go to 0. But just wait till that happens. Okay, that's it. I don't think there's anything else here. Let me just make sure there's nothing else. I'm not going to plug in the 0.001, okay? I'll let you do that on your own. Do part C on your own. All that would change is this would be 1.01. This one would be 0.01 and everything else, and you should get as an answer 3.01. All right, we're going to move on. Yay, we're out of 3.3 finally. Let's go to 3.4. Ah, 3.4. This is going to go quick, but I need you to pay attention. There's a lot of information in a very few notes. Everyone have 3.4 with them? The library of functions. This section covers library of functions and piecewise functions. We are actually, are you looking for 3.4? I have an extra copy right here. Anyone else? Okay, this section covers library of functions and piecewise functions. I have chosen that I'm going to do just library functions. Then we're going to go to 3.5. After we finish 3.5, we're going to come back to 3.4 and do piecewise. All right? That's the order. So library of functions. These are the functions you should all know. All right? In other words, you should know what the graphs look like. Oops, that should say domains. What the domains of these graphs are, what the ranges, etc. All right, first function is f of x equals x squared. This is called the squaring function. We should all know that it looks like this u, which we call a parabola, and it has as this lowest point, right? That lowest point, which we'll call later a vertex, it touches the origin. The origin is 0, 0, right? Everyone needs to know what that function looks like. X squared. The next function we need to know, oh, oops, I forgot to put constant. Let's do a constant function. Constant function is I heard straight line, but like f of x equals 3. It's just a flat line, horizontal line that goes through 3. All right, that's what a constant function looks like. F of x equals x. F of x equals x is the diagonal line called the identity. We call it the identity because whatever you plug into the function, it spits out. If you plug in 2, it spits back 2. You plug in 3, it spits back 3. You plug in -5, it spits back -5. So it's identical, right? It's a car wash that doesn't clean the car. It just returns the same dirty car. So that's our identity function, but it looks visually like a diagonal that goes through the origin, doesn't it? Then we had the squaring function, which we just said, that's x squared. Then we have, these are all in the book, by the way. You don't have to worry too much about, trying to copy these all down. The cubic function, x cubed. It starts off down at the bottom, right? Comes up, passes through the origin, goes up on the right. It almost looks like a parabola where one side just got flipped over. It's not exactly that, but that's kind of what it looks like visually. So that's cubic. Is that what? This would be an odd function, yes. And coincidentally, what is the power on the cubic function? It's odd. That's not a coincidence. That's actually part of the reason why. But there are functions that are odd that are not power functions, where they're x to powers. Like, well, stay tuned. Pre-cal. Okay, the square root function. Okay, this is the first function that we have that has a domain problem, a domain issue. Right? The square root, you can't take square roots of negatives. So the graph should only exist from 0 to the right. So this one almost looks like a parabola that half of it's been cut off and it's been like laid on its side. But again, notice that the origin is included in this function. I'm going to back up. Constant function. What's the domain of a constant function? The domain. Negative infinity to infinity. What's the range of a constant function? It's whatever its value is, and it's a single number. So if this is the function f of x equals 1, the domain is everything, the range is the number 1 in braces. How about the identity? The diagonal. Domain, everything. Range, everything. All real numbers, negative infinity to infinity. How about the squaring function? Domain, everything, right? Negative infinity to infinity, because it goes up forever. What about range? 0 to infinity. Include 0 or not? Included. How about cubic function? Domain, everything. Range, everything. Yes. 0 squared is 0 still. Square root. Domain, 0 to infinity, including 0 or not? Yes, you can take the square root of 0. The square root of 0 is 0. So 0 bracket to infinity. And then range, 0 to infinity also. Because it does go up. It keeps going up over here slowly, but it does go up. Next thing. Let's make this a little bigger. The cube root function. Looks a lot like which one? The cube, x cubed. It looks like x cubed. You can take a cube root. Remember that we don't have problems with domain with cube roots. With odd roots, we don't have that issue. So everyone here needs to know what this looks like, all right? Cube root. What's the domain? Negative infinity to infinity. Range, same thing. It also passes through the origin, right? Notice I put that dot at the origin because it seems to be in most of these, doesn't it? Okay. Next one, the reciprocal function. The reciprocal, remember reciprocal is you flip the fraction over, right? So like if I give you the number 2, the reciprocal would be 1/2. I give you the number 3, the reciprocal would be 1/3. So all you're doing is just putting 1 over that number. That's what this is. F of x is 1 over x. And let's take a look at what it looks like. So you cannot plug 0 into this, right? According to the picture, what happens here is to the left, it looks like it's getting closer to 0, right, the x-axis? But it never hits it. And as you get closer to 0, what happens? It dives down, and you have what we call a vertical asymptote. We'll discuss those more later also. At 0, you cannot have anything. Asymptote. Asymptote. There are different ways to say it. I mean, the P is silent. Asymptote. Yeah. If you say it fast, no one cares. Asymptote. Okay, that's the question. I have this dot here, but it is not part of the graph. I have it there because I want you to see that this graph almost kind of has like a center to it. And what we're going to do in a little while is we're going to move it around. So we're going to take this graph and we're going to move it up. And I'm going to try and get you to see that the center point moves with it. Okay? But that's later, okay? It's not exactly, we're not there yet. Okay, let's talk, what's the domain of this regular reciprocal function 1 over x? Well, the blue goes to the left forever, but when I get to 0, I have division by 0. I can't have that. So take 0 out. To the right of 0, everything's good. All real numbers except 0. So you could just say x can't be 0, or you could say in interval notation, negative infinity to 0, parenthesis, union, parenthesis, 0 to infinity. Either way. This is the first one where we have kind of a weird issue with domain. Just pay attention to the picture, though. From the left, go out the left, it heads towards 0, right? As you go towards 0, it heads to, where's that? Way down there. Negative infinity is where it's headed. On the right side of 0, as you go out to the right, it heads towards what? Well, the graph's going out to infinity. What's the value? What's the height of the function headed towards? 0. Over here, as I get closer to 0, the function's height is headed towards positive infinity. It's a very important function in mathematics. We use this a lot, all right? So what is the range? Well, you can have all negative values, right? Until you get to where? 0, 0 is not there. And then you jump over 0 and you go from 0 up. So domain and range would be the same in this problem. All right, the next one, the absolute value function. And it looks like a V. It is not a parabola. It's a nice, sharp corner here, all right? The absolute value function to the right of 0 is just the identity, right? What's the absolute value of 1? Absolute value 2. That's the same thing the identity function is doing, right? 1, 1, 2, 2, 3, 3. The only difference is that when you go the other direction, you plug in negative 1, it spits back positive 1. Negative 2 spits back positive 2. So all that, imagine the identity function, the identity comes down, doesn't it? Just imagine taking that down part and reflecting it up to positive values. Reflect it up and you get the V. Y'all see that? Okay. So that's what an absolute value function looks like. What's its domain? Everything, right? What's its range? 0 to infinity. Also, we notice it has the origin there at that corner. All right, the next function is one, any computer science people here? No computer science? 1, 2, 3 maybe? All right, this is used in computer science a lot. It's called the greatest integer function. This is, what it does, it's hard to, I think the first time I ever saw it, I was like, what? Here's the graph of it, okay? But let's figure out what the hell it's doing, all right? This function, which has different notations, all right? Int x is the way this book refers to it, int x. 2 brackets around an x. Or in computer science, like in my program Mathematica, floor x is the function. So let's try and figure out what's happening. It returns to you, you plug in a value for x, right? It will return, it spits out the greatest integer less than or equal to x. What's an integer? What are the integers? They're counting numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Including 0 and your negative numbers, negative integers, negative counting numbers. So all integers are like negative 1, positive 1, negative 2, positive 2, negative 3, positive 3. All those are integers. So this function is a car wash, basically, where you give it a number, and it's only going to spit out an integer. And the integer that it spits out is the integer that is the greatest integer less than or equal to the number that got plugged in. What the hell? Okay, so let me give you an example. What is the greatest integer function of the number 3. Okay, so what's the greatest integer you can think of that's less than or equal to 3? 3 itself. Okay, how about 3.1? What's the greatest integer you can think of that's less than or equal to 3.1? 3. The greatest integer you can think of, right? 3.72. What's the greatest integer less than or equal to? 3 again, right? 3.999. What's the greatest integer less than or equal to 3.99999? 3 again. It's going to be 3 the whole time until I get to where? When I actually get to 4, it's going to jump to 4, isn't it?
Rounding off.
But it's not rounding up or down. It's always rounding what? Down, to the floor. Does that make sense? To the floor. There's another function in math called the ceiling, which does the opposite. It returns the greatest integer the least integer greater than or equal to your x. So, but that's used less often. But imagine just rounding up all the time. That's ceiling. Rounding down all the time would be floor. So if I look at the graph again, does it make a little more sense? Look, oh wait, 3's not over here. Shit. Well, I can't really put it in there. Imagine this is 3, okay? Imagine that's 3, imagine that's 4. We said if you plug in 3, what do you get? 3. That would have been here. See, it's a solid dot? If we plug in 3.1, we get what? 3 again. We plug in 3.5, 3 again. 3.99999, 3 again. When we get to 4, now this is 4, we're acting like this is 4, where would I be? Up here at 4 to the next place, which would be right up here. I would draw a solid dot. The open dot means what? That you're all the way up to that point, but not actually at that point. You're undefined, so it's a circle. We just represent that open hole to mean is all the way up to there, but as soon as you get there, remember this talked about how many points, how many numbers are there? So you can go all the way up to 4, but as soon as you get to 4, you have to jump up to the next one. So it looks like this. We call these step functions, right? How about this? Let's try this one. This one's a little more tricky. How about negative 1.5? Or let's say negative 1. What's the greatest integer less than or equal to negative 1? Negative 1 itself. So if you're at an integer, it spits out exactly that integer. How about negative 1.2? Negative 2. Negative 2. Why? Think of the number line. Negative 1, negative 2. Less than is to the left, greater than is to the right. Right? So if I am here at negative 1.2, what is the greatest integer you can find less than or equal to this number? That means I have to look this way, don't I? And it's negative 2. The negative the negative is tricky. It's easier when I'm over here, right? At 3 and 4. When I'm at 3.5, what's the greatest integer less than or equal to 3.5? 3. But here, you're still going to the left. It would be negative 2. Does that make sense? Okay, negative 2. Always look to the left, but then you have to draw something, right? All right, so there's your picture. All right, that's it. That's the only notes for this first part. Now just do 19 through 16. That's going to be difficult. That's not what I meant to say. Do 19 through 16, but just the ones greater than 20. Does that make sense? What I meant to say was 9 through 16. We will do the rest after we do 3-5, which is what we're about to start. All right, let's open the poll here. Let's just take a quick little snapshot. Wait, you're voting? I didn't ask you a question yet. Hold on. Okay. Do you think you can memorize those graphs by next class? Yes? How many are there? How many were there? Including this step function? Yeah. Okay. Let's move on to the next note. Everyone has 3.5 notes. 3.5. All right. Now, here's the deal. If you know what a function looks like, which I just said, I just gave you a bunch of functions that I said you need to memorize, right? If you know what a function looks like, and this goes for any function, doesn't have to be those functions that I just showed you. In pre-cal, if you have a sine curve and you know what it looks like, then this set of transformations will work for all functions. What this allows us, this section is about, is taking a function we know and transforming it into something more complicated. Or another way of looking at that is, if someone gives you something that looks complicated, can you connect it to something more simple? So given a function f whose graph is known, yes, x squared, you know what it looks like? Yes, parabola. Square root of x, yes, it looks half laid on its side, right? That's your square root of x. Absolute value, okay? If you know what a function looks like, then the transformations of those are as follows. If you'd like to take your function and do a vertical or horizontal shift, vertical meaning up and down, right? Horizontal left and right, then here's how you do it. Take your function, add a number to it. If you add a number to your function, it'll move the function up by that much. If you take a function and you subtract a number from it, it's going to take that picture, whatever you know, and it's going to move it down. That make sense? That's pretty simple. Add a number up, subtract a number down. Now, if you want to move it left and right, it's actually opposite of what you would think. If you add the number, I'm going to say h, inside the function, notice the difference. That h is being added in the parentheses with the x, as opposed to the k, which is outside the parentheses. See the difference? I'm going to give you an example, but do you see that in the notation there's a difference? Adding a number outside the function goes up. Adding or subtracting a number outside the function goes down. Adding a number inside does what according to what I say there? What does adding a number inside the function do? It moves it to the left by that much. So you would think positive is to the right, but with left and right shifts, which are called horizontal shifts, it's opposite of that. So if you add a 3 inside the function, you actually go to the left 3. Now if I subtract a number inside the function, that will move me to the right 3. So just keep that in mind, make a little note there, opposite. Then we have what are called vertical and horizontal stretching or compressings of the graph, which means that we are going to scale the graph. We're going to, instead of moving it up, down, left, right, we're going to stretch it out, or we're going to compress it down. Flatten it out, widen it, okay? We can do that to achieve it. Here's what we do. If we put a number in front of the function, a, and we multiply it, so that could be like 2 times the function. If that number we put in front is bigger than 1, it is going to have the effect of vertically stretching it. It means stretching it out. Not moving it up, stretching it. Taking all the points and scaling them. Now, if we put a number in front of the function that is between 0 and 1, so like 1/2, something like that, 1/10, instead of stretching it out, it's going to do what? Compress it vertically. Okay, move everything down by that much. By scale it, factor it down. Not move it down, compress it down. Now, we can also do compresses horizontally. These are a little more complicated. This is going to come up in pre-cal quite a bit. If you put a times x, with that a being bigger than 1, what it's going to do, again, this is kind of opposite of what you think. So like if I put a 2 in here, you would think maybe the 2 would stretch it out by 2. It actually compresses it by 2. To get it to stretch, you actually have to put a number in there that's between 0 and 1. It's like 1/2. That would stretch us out horizontally. And then the last two things that we could have are reflections. If you want to take a function and reflect it over the x-axis, you just put a negative in front of it. And it takes the whole graph and reflects it over the x. If you want to do it over the y-axis, you put the negative inside the function. Okay? Those are all the different transformations. Now let's see if we can make any sense out of this at all. All right? Let me start this notebook over. All right, here we go. I'm going to start with the constant function. And let me make this a little smaller. Oh, you know what? Let's do this. I'll bring up my notes over here so I can write something down. Okay, here's what I'd like for us to look at. Let's start with the identity function. That's kind of boring. Let's do the squaring function. Okay, that's x squared. Yes? So I'm going to jot down over here, this is f of x equals x squared. Tell me what the function would be, a different function that would be that picture but moved up 3. X squared plus 2? That would move it up 2. I said 3, but that's okay. It's all right. If I want to move that g of x, I'm calling it something different than f. This x squared plus 3 should look like that picture, what, shifted up vertically up by 3. There's 3. Now I'm going to show you the function. Here it is. X squared plus 3. There, that blue one is that transformation. Yes? Okay. Now let's try something a little different. Let's move it instead of, get over there. Instead of moving it up 3, let's move it to the right 3. I'll call this H. So what's the difference? Remember I was saying the number is inside or it's outside? Okay, to be inside, what we mean is this. The part of the function that's creating the parabola is the squared, isn't it? The x is here by itself. I need to put a 3 next to it. But do I add it or subtract it if I want to go to the right 3? Subtract, opposite of what I think. So I'm going to do x, what? Minus 3 in parentheses, and that's it. That should have the effect of moving it to the right 3. See the difference between these two? Yes? Now, let me check that. I'm going to actually move it to the right 3, so I need to there we go. Look at the function. X minus 3 squared draws this blue one. That's what we wanted, right? Okay, questions? Okay, this time I want you to move it down to the left 4. Down to the left 4. H-I-J, I'm going to say J instead of. What are you saying? X plus 4 squared minus 2. So I said I wanted it to go down to the left 4. You're saying this should do it? This right here has the effect of moving it to the left 4. This is down 2. Let me check it. So if I go right, does that match what we have here? Yep. Okay, so that looks good. Next one, I think I'll write down what I want first because it's going to be a lot. I want you to go to the right 2. I want you to reflect over the x-axis. I want you to go up 3. So give me everything that's going to make this happen. I'm going to call this k of x. Negative? Okay, you want negative, then what? X minus 2 squared plus 3. Let's take a vote if you agree with this. You all agree? Okay. So look at this. This is critically important. When you do transformations, the order of operations is followed. So when you do order of operations, what are you supposed to do first? Things in parentheses. This would be the first thing that happens. Then squared, which would create the parabola. Then what? The negative 1 is multiplication. That would happen before this because that's addition. So what would the negative do? Flip it over the x-axis. Then add 3. Do you understand? Because if you change that order, you don't get necessarily the same thing. Let's see if we agree. Well, let me check that this is right. We want it to the right 2, so it should have been there. We wanted it up 3. Should have been there, and it should have been reflected over the x-axis. Yes. So that's the picture. Now, does this match what I have here? Just imagine that 3's in the back as a positive 3. It's right. That's kind of the limitation of my system. I didn't want to waste too much time getting this order switched around. This is negative x minus 2 squared plus 3. Okay? Now, let's talk about a stretch. I'm not going to give you a problem where I stretch it, but let's discuss the stretch a little bit. Let's quit the reflection there. I mean, yes, you could have stretching. I'm just not going to do a bunch of examples. I just want you to see it visually. What we said about the stretching was that if I chose a number that was, what, bigger than 1 and multiplied it in front of the x squared, it would have the effect of stretching it vertically. So here's my stretch. Right now the number in front of it is a 1. I'm going to stretch it up to a, ooh, I didn't want that. How about 2? 2x squared. See the blue one? The stretching had the effect of making it more narrow. If I change it and make it a bigger number, like, look what happens to that blue one. You see that? It's almost like you've taken these 2 red points at the end, and you've taken them way up there, and by doing that, it pulled the graph in and made it more narrow. So that's what the effect of a number in front is. Now, what would happen if I made it a negative number in front? It would be negative. All it would do is just flip it over the x-axis. So it would still be real narrow, but it would now be facing down. Understand? Okay, don't want this anymore. How about if that number in front is not bigger than 1? So now, you see that? It stretches it out horizontally, pulls that parabola apart. I think that's good. Now that was the square root. How about something like this? What function is that? Square root. Okay, this time I'm going to do something different. I'm going to show you the graph, and I want you to tell me what the function is. Instead of me giving you what I want the shifts to be, I'm just going to draw it. And can you all see that? I need to make this a little bigger. Okay, so what is it? X minus 4. The square root of x minus 4, right, plus 4 would give you this one. Let me give a new page here. And let me go a different color. So this blue function right here, we have to first identify it's a square root function. We have to realize it's been moved to the right 4 and up 4. To move it to the right 4, we need to have a what inside? Minus 4, opposite of what we would think. Then to move it up 4, we do plus 4. Call this f, sorry, f of x. Should have given myself some more room. I'm just going to put f of x over here. Okay? That would be that blue one. Everyone good with that? Okay, how would this change it? Ooh, now hold on. Be very careful here. Make sure you get this right. All you need is a minus on the outside. Let's see if that would work. Would this be correct? Would that work? Order of operations. Starting out in here, you move to the right 4, right? Then you draw a square root function. Yes? Then reflect it over the x-axis. So let me bring this thing back. Take my time here. Square root of x, yes. Okay, so this minus 4, that's what it does, right? Then the reflecting over the x-axis does this, and then moving it the up 4, put it there. Yes? That work? Okay. You have, no, it's the order of operations you've been following your whole life, right? Parentheses first. So you want to visualize that this right here is the, like the parentheses, that's the inside the radical. You do that first, then you do exponents, which in this case, square root is an exponent. It's 1/2 power. And then you do multiplication. This is like -1 times something. Then you do addition. Yep. Please excuse my dear Aunt Sally. What else is there? PEMDAS, right? How about I give you another one? Let's see if I can, I'm going to see if I can stump you or not. Okay. What's the function you should recognize this as being? The reciprocal function. So I know that this has something to do with 1 over x. Now let's talk about the shifting. Looks like it's been moved 1, 2, 3, 4 to the left. And then, so how do I write that? What's 4 to the left? 1 over x plus 4. Look, down there next to the x. Not separated, down there next to the x. Then how do I move it down? 1, 2, 3, 4 again. Is that what I should do? Yes? What about, did I flip it? I did flip it over the x-axis. Could you see that? Do you see that this left side goes up, right side is going down like this? On the red one, the left goes down, the right goes up. Do you see that? So I had to flip it. So I need a negative where? On the outside right here. And then you can have your -4 out here. In this particular problem, if we flip over y, it should be the same as flipping it over x. Yes. So am I missing anything? Let's check it. That's it, right? Right here. So you need to be comfortable both ways. Someone gives you a function, you sketch it. Someone gives you a sketch, you give the function. How do you know? They would both work. If you put the negative down here. Yeah. But you'd have to be concerned. Look, there's a subtlety in this, all right? Let's address this. Let me go back to the original here. All right. Do you agree that this blue is a reflection over the x-axis and the y-axis? Yes? But if I move this, let's get this out of here. If I take this right here, and I say reflect that over the y-axis, right? The y-axis, what would it be? If I move it first, then reflect it over the y-axis. It's going to be over here, isn't it? It's going to go like this and go down. This top part right here gets moved all the way across to this side and goes like this. That's a different effect than flipping it first. If you flip it first, then move it, it's a different effect. I need to do it on a different page so you can see what I'm talking about. Okay, start from scratch. No, we're not even going to do that problem. Do something a little more general. Okay, what if I take, what am I doing on time? I'm good. What if I take this function right here, and I say to you right now, move it up 3. Then you do this. Yes? And maybe you would think to yourself, that's just x squared plus 3, right? Then I say, reflect it over the x-axis. What's it going to do? This point right here gets moved all the way down here, right? This point up here gets moved all the way over here. So whatever the distance is from here to here, it's that same distance the other direction. So you get, in effect, a parabola that looks like this. So how would you write this over here? You put a negative in front? Like that?
No.
That doesn't work. Do you see that that is not correct? This is not correct. This is where the order of operation comes in. If I say, take this green one, move it up 3, I agree that this is the picture. But if I say, then reflect it over the x-axis, like this is not the function that represents that. What does this one look like? So this is not right, wrong. So this one should, what is this one? Order of operations starts as a parabola, then what? Flip it, which would make it this, then what? Up 3, which would put it right there. That's a terrible picture, but that picture is not this one, right? They're not the same. This blue one's up here, this one's here. That's because the way I told you was I violated the order of operations when I said it. I didn't violate it. I could still tell you to do this, but now you have to realize that this isn't going to work. So you would just, if I were looking at this, I would say, okay, look, this is the green one. It got flipped over first, then moved down. I hope that kind of clarifies a little bit of what was brought up. Yes? Right here? Like, let's say that that was like a -3 here. Then that would just make this thing more narrow. Well, if there was a 3 up there, it would just make this thing a more narrow-looking parabola. But it would still be a parabola. It got stretched out. That's going to be impossible to go back and look at if you ever look at that. Okay. All right, let's see what I had in my notes here. Was there anything else in here? Okay, so these are some examples. Let's talk through these. What's this? Part A, what's this? Parabola, move down 2. This one, parabola moved right 4. Can you find the domain of these in range as we talk through this? Maybe I can do the first one. I'll just do, how about I do the most complicated one? Huh? What did I say? 4. The squared is what gives us the shape. Okay? How about I do this one, I graph it and tell you domain and range. But finish this off. This one right here, what is this one? Parabola, right 4, down 2. Okay. This one, tell me what it is first. Parabola, right 4, reflected over the x-axis because of the negative, and because it's a 2, stretch to make it narrow, and then up 5. Okay, so let me draw that one for you. I have, let me just do instant grid paper here. That's right. It's not exact. Yes, it's a very subtle thing, and I'm not real particular on that. It's impossible to be real particular on that. All right. So I had a parabola, right? I like to do them dotted. And what am I going to do with this? We said first thing was to the right 4. So I like to take that point there. 1, 2, 3, 4. Here it is. Here's my new parabola. Now, reflected over the x-axis. So I'm accounting for the negative now. Then stretch it by a factor of 2. So imagine taking these 2 points and pulling them down by doubling how long they are. So how long does this look like it is from here to here? About 3. I'm going to now move it to about 6 because I'm doubling it. So that edge is going to be about here, that arrow. This arrow here is going to get pulled to 6, and now I'm just going to draw my U like this. I hope that makes sense. It's not a perfect science on the stretching. Then, the whole thing up 5. So notice this point right here that started here, went here, and then when it got flipped over, it didn't move, right? When it got stretched, it didn't move. Now I'm going to move that up 1, 2, 3, 4, 5. Here it is. This is going to be my final answer. So 1, 2, 3, 4, 5. It's up here. And it's this blue one, you know, sketched out. Doesn't have to be perfect. We're not landing a man on the moon here, okay? It doesn't have to be exact. We are just getting a basic idea of what this thing looks like. And what's most important to us is actually the domain and range. What's the domain of that function? Everything, right? What's the range? I'm going to say all real numbers. Ooh. I never get bigger than what? 5. But I'm everything below that, right? So I say what? Negative infinity to 5. Including 5 or not? Yes. See how that works? Yes, but I'm only using these just because I didn't want a bunch of graphs. So I'm just dotted to show here's the beginning, the next phase, the stretch, and then the final one is solid. But normally dotted means don't include the boundary, like don't include the curve. All right, so that's this. See, now let's go back again and let's talk about what the value of that quick sketch was. Is it possible, can anybody tell me right now, if it's possible to plug an x value into this function right here and get the number 7 to come out? Not what number do I plug in, but is it possible? Can you tell me for sure, is there a number x that I could plug in and get 7 to come out? To come out is the range, right? Well, what did you just tell me here? The range is everything below 5, right? It's impossible for that function to ever achieve 7, isn't it? And that's very difficult to say visually by looking at, well, it's more difficult to just look at the function and be like, oh, sure, 7 never comes out of that, right? But as soon as you have the picture, it's automatic. Does that make sense? Is it possible to get 0 out of this? Yes. In fact, there should be 2 places where we get 0 to come out, right? Right? There's somewhere. So there is value in finding a quick sketch of a function and then its domain and range from that. Okay, let's talk about these, and maybe I'll do the last one. Do we have another one after this? Oh man, we got a lot more. Okay. We'll just talk through these. This is what function? Square root. We all know what that looks like. Okay. Down 2, right? This one? Right 4. Right 4 down 2. Right 4. Careful, hold on. 1/4. What does that do to it? It spreads it out horizontally. Okay, again, that won't be a perfect science. You'll just have to kind of imagine stretching it out to the right. And then lastly, up 5. Would you like me to sketch that one or not? I'm getting yeses and nos. I'll go yes. That last one. Okay, it was square root function. Here's square root function. I'm going to move it to the right 4. It's terrible. Stretch it horizontally this way. I don't stretch it to the left. There's nothing to the left. So it's just going to look more like, imagine taking this point and moving it this way. So it's going to still go towards that. It's widened. Stretch it horizontally. How do you, I can't move this point. What was the number we had in front? 1/4. So imagine however high this point is, right? It's now 1/4 of that. And however high this point is, it's 1/4 of that. However high this point is, it's 1/4 of that. Pardon me? Compressing it vertically is the same as stretching horizontally. Either way, you can look at it both ways, right? If I take a parabola, right? If I do this, one person would say, I've stretched it horizontally. Another person might say, I've taken it and squashed it, compressed it vertically. The numbers in front, the stretches and compressions are tricky because they're hard to draw, right? Let me finish the last transformation here. Up 5. Up 5. 1, 2, 3, 4, 5. This will be my final picture. It's kind of this narrowed out square root function. Again, domain, though, is quick. Domain is greater than or equal to 4, including 4. Range, 5 to infinity, including 5. All right, suppose the x-intercepts of the graph of a function f of x are -8 and 1. Y'all know what the x-intercepts of a graph are? Where it hits the x-axis. Okay, so it says suppose that this is true, and then figure out what this is. So let me graph this. -8 and 1. I have a function. Oh, that looks a little crazy. -8 and 1. 1, 2, 3, 6, 7, 8. Here's an x-intercept, and 1, there's an x-intercept. That's all they tell me about this function. Those 2 points are on the x-axis. Then I'm supposed to figure out from that what are the x-intercepts of the function f of x plus 4. So what does f of x plus 4 do? That moves it to the left by how much? 4. So the x-intercepts, guess what happens to them? They move to the left 4, which means they're going to have the effect of screwing up my picture because it's off the graph. All right? So I take these points, I move it 1, 2, 3, 4 here. Move this one 1, 2, 3, 4 here. So the x-intercepts of that graph are what? -12 and -3. And that's what it's asking, right? What are the x-intercepts of this function? So what are the x-intercepts of this one? This time, instead of going to the left 4, we go to the right 3. So what would those be? 1, 2, 3, and then this one 1, 2, 3. So this one's 4, and this one is, what was it, -5? This making sense, y'all? Yes. Next one. What about this one? 2x. How do you mean? What does that do? 2x is going to double. Does it? Interesting. Interesting. Getting. Okay, look at, let's start with the original idea here. This right here was at -8, wasn't it? So what we knew is that f of -8 was 0. The other one told us that f of 1 was 0. They want to know what the x-intercepts of f of 2x would be. We want to know what makes that happen. So I know if I can get an 8 in here, it's going to spit out 0, right? If I can get an 8 inside of this function f, it's going to spit 0 out. So if I double the value in there, I can't plug 8 in right here because that'll give me -16. What do I need to plug in right here to get -8? -4. Right? If I plug -4 in here, 2 times -4 is -8. And we know that f of -8 is 0. Halving it. I'm trying to show you algebraically why. I know that f of 2 times -4 is the same as f of -8, which I already know is 0. So that means -4 is an x-intercept of this new function, f of 2x. And that means that from this one, what would have to happen? Half or 0.5 would be the other one. So by doubling inside, your x-intercepts are scaled by half. So the two x-intercepts we would have would be -4 and 1/2. We compressed it. We compressed it. Look, we took the 2 blue points, right, and we moved them in by a factor of 2. We cut them in half. So instead of being out there at -8, it's now at -4. Instead of being out there at 1, it's brought into 1/2. Okay, what about the last one here? What's f of -x? Reflection over the y-axis. So how would that change my x-intercepts? The one that was at -8 now goes over the y-axis to the +8. The one that was +1 comes over to -1. So the two x-intercepts from that one, for these two, or the x-intercepts here would be +8, -1. This was -4, 1/2. Well, we already wrote those down. I like this one. Given this graph of f, graph the following. See if there's anything after this. Yeah, I need to do these today. I think I want to try and make this a quiz, but I don't know if we'll have enough time. Let me get to these examples. We'll come back to this one, because I think everyone in here, from my feeling of looking at you, I don't know if it's just because you're ready to get out of here, that you're getting the idea of moving things up and down and left and right and what would happen here. So here's something a little more difficult. Given this function, use completing of the square to graph it with transformations. Very useful later and today. So let me start a new page. Let me write down the functions. How many of you have some experience with completing the square? You can just raise your hand or say yes. completing the square? No? Okay, let's do a vote. How many of you have done completing the square? Or are y'all just telling me no? You've heard of it. Okay. You were drunk doing math? In class? All right, so what we would really like is if it looked something like where we had the x squared plus a number like 2 and maybe x minus 4. If it was like this, we'd be able to do it pretty quick, right? Move it around. The problem is it doesn't look like that. And the biggest issue is this 4x. So what we do is we do this thing called completing the square. And here's the technique for completing the square. It'll come up in almost every class you take from here on out. To complete the square, you have to be looking at a quadratic trinomial. That means your variable is squared, and you have 3 terms. The power comes down, x squared, then an x term, then a constant. When you have this, you first put it in descending order. It means highest power of x down. Anybody want to tell me what you do? First step to complete the square of something? No? You always first make sure that the leading coefficient is 1, which it is in this case. That's always the first step. After you've figured out that the leading coefficient is 1, if it is, you then take a look at the coefficient of the x term, which in this problem is what? 4. You will always take that number 4 and you will divide it by 2, and you will tell me what that is. 2. Okay. Always divide by 2. Then you will take that 4 divided by 2, same thing you just had, and you will square it this time. So that's just 2 squared, which is 4. What we have created here are 2 numbers, a 2 and a 4. One of them we got from just taking 4 and dividing by 2. The other one we got by taking 4, dividing by 2, and squaring. These are our 2 magic numbers. We have to use these numbers to do completing of the square. If you're interested why this works and stuff, come to my office. We can talk about it. It's a little more theoretical. We don't have time for it. So now I'm going to do something very clever. I'm going to force everybody to see that we have a hidden 0. I remember in class the other day someone had said something about it was like a hidden 0 or something, and I had mentioned that we always have a hidden 1. We always like to come in with a hidden 1 like something divided by itself. You know, we've been doing that for a long time, getting common denominators, multiplying top and bottom by something. Remember that? Realizing that next to everything is a plus 0 is an even more advanced mathematical skill. And it took somebody a long time to figure out that this would work, all right? So this 0 that's sitting here, I want to rewrite it, but I want to use that second magic number. I don't like to call magic numbers. The second number that I got, which is the 4. How can I rewrite 0 using that 4? Can I do this? I could do that, but how about plus 4 minus 4? Plus 2. Isn't plus 4 minus 4 still 0? So I haven't really changed the problem, have I? I just made it look a little different. Now, in this, by doing that, what you have done is you have automatically, by default, the way this thing is designed, you've created the first 3 terms will guaranteed always factor. It's a perfect square trinomial. All right? And here's what it will turn into. Here's where that first magic number comes into play. This will always turn into a set of parentheses with squared. What goes inside of this is always going to be x, and then guess what? That first number. So was it positive? Yes, so I put plus 2. Now, if you don't believe this, take x plus 2 on the side times x plus 2, FOIL it out, and you will get these 3 terms. You all believe that? Okay. Now, what's still out here, though? Minus 4 plus 2, which is negative 2. And guess what? This is a parabola that's been shifted which way? To the left 2 and down 2. I've got my sketch. You see that? Okay, because these two pieces come together to give you that. So I can do a quick sketch from this now. Parabolas move to the left 2, down 2, like this. Now that's the easier completing the square. Let's look at a more advanced one, which would be this one. Negative 3x squared plus 6x plus 1. So what's the first step for? You have to have a 1 on x squared. Okay, divide everything by 3, negative 3. You could do that if you had an equation. You don't, I mean, you technically don't have an equation here. You have a function, don't you? Okay, now there's something subtle here I want to talk about because this comes up a lot in my Cal 2 class. I have this discussion with my students. How many of you have learned completing the square where you got that number that I showed you a second ago, but then you like added it to both sides of the equation? You all remember that? Okay? I would throw that out. Just take that out of your brain, okay? The reason why is because like in this case, you do not have an equation to work with where you go both sides. And later on, in Calculus 2, even in 1, you don't have an equation to work with. So the hidden 0 is the way we go at it. All right? So here we go. So I can't divide by negative 3. But what I can do is just factor negative 3 out of just the first 2 terms, and just tell me if you agree that that's the same problem. I haven't done anything except pull the negative 3 out of the first 2 terms. Yes? I left the 1 alone. I'm not even touching it. Okay. Now, you see this thing inside here? I'm going to complete the square on this. Okay, what is the number in front of the x term? Negative 2. I'm going to grab that number, and I'm going to divide it by what? 2, always by 2. Figure out what that is. In this case, negative 1, right? Now I'm going to take that number, negative 2, I'm going to divide it by 2, and I'm going to square it, and that's going to be positive 1. Those are my 2 magic numbers. Can I stop saying magic numbers?
Yes.
I feel like we're in like some kindergarten class when I'm saying, they're magic numbers. Okay, these are our 2 numbers that we'll use for completing the square. So I now have to realize the hidden 0. Where is it, though? So here, here, right next to the 2x is where it needs to be. Why? Because if you put the 1 out here, right, if you put a 1 and negative 1 out here, then you cannot combine. Remember how we said one of them is going to give you the perfect square trinomial? If your 1's out here, it's not next to these. Because technically, you can't touch these until the negative 3 goes through. That make sense? Okay, so let me rewrite this. Here comes my hidden 0. A very advanced thought. We have to give ourselves credit as human beings. Realizing a hidden 0 was a big deal when we figured out we could do things like that. Kind of like making tools and stuff. All right, so I'm going to replace that 0 with, so do I go -1 + 1 or +1 - 1? Does it matter? It's always this number minus this number. So you always put the plus here. Plus 1, I'll do it in black. Plus 1 minus 1. There's my hidden 0. Close the parentheses, plus 1. I know some of you are going to be kind of, resistant to change, and you're going to want to do the one on both sides of the equation. I'm telling you, you can't do it here. There's no way to do it safely. So come along for the ride here. So then what are you going to do with the minus 1? Are you going to remember it's there? Right? This plus 1 is going to be peeled off with these to create 3, but that minus 1 is going to be here. In addition to that, that minus 1 can't get out of this parentheses until we do what? Realize that that negative 3 has to hit. So it becomes kind of dangerous to try and do too much in one. Okay, I'm running out of time. All right, watch this. I know that these first 3 terms are going to turn into what? A set of parentheses squared. What goes inside? X, and then using the first number I got here, minus 1, that should be the factorization of these 3 terms right there. I still have next to it minus 1. At this point, you cannot just say, okay, it's just this shift and all this stuff, because you got a lot happening here. You've got this negative 3 times all of this junk, then you have a negative 3 times this, and then you can free it from this red parenthesis. Do y'all see that? So let's distribute the negative 3 through. It'll be negative 3 x minus 1 squared. I'm not even going to do anything with that. I'm just saying it's this times this, whatever it is. This times this, which is positive 3, and then plus 1. And that you can combine together, negative 3 x minus 1 squared plus 4. That looks like something I can graph, right? Parabola, it's been moved to the right one. It's been reflected over the x-axis. It's been stretched by a factor of 3 and then moved up 4. If I'm not mistaken, that's the end. You should be, so on the 3, 4, remember on 3, was it 3, 4, you only doing that 9 through 16? On 3, 5, you should be able to attack everything, all right? Next class, we're going to come back, and we're going to go back to 3, 4 and finish off piecewise functions. Then we'll start chapter 4, quadratics, and then equalities. We're going to be in good shape. Man, we have to have a quiz. I think I feel like we've caught up. So let's guarantee you a quiz next class. Anything from the last quiz to now. We will not have piecewise functions. Yeah. Yeah, I think the last one was, what was the last quiz we had? It's a group quiz, yeah.